Yeah, first time for real for me in Kufstein. So I have been spending 2+ years in Innsbruck, but I never managed to stop at Kufstein except for a train change. So, but now I'm here and I'm very much looking forward to this tour we are going to have this afternoon. So the title is also a little bit clunky, and I hope you are all kind of in the mood for another gear change just before lunch. So I could also have called it Fun with Quantum Trajectories, and I try to avoid too much technical stuff. So if you are too tired, just don't look at the formulas and hear what I have to say. And I hope I can convince you that this is some interesting stuff that we are doing, which is related to the dynamical phase structure of open quantum systems and how you can simulate them, in fact, on quantum simulation platforms that are around. So this is Tübingen, so this is where I'm from. I just want to say people involved are Marcel Zech, who's a PhD student, and Cecilia De Fazio, who's a postdoc Humboldt Fellow in our group, and also Federico Carollo, who's now in Coventry, and this has been done also in collaboration with Marie-Carmen Banyuls and Maria Thea. They are both at MPQ Garching and also, I think, involved in this cluster. And I'm happy that we can all be happy together, because Tübingen is also very happy about how they fared in this cluster competition. So, and now let's get started. So, what I want to tell you about is basically listed here. At the beginning, I want to make a case that kinetically constrained systems are interesting. I will introduce what kinetically constrained systems are very briefly. And basically, the take-home message of this is that if you look at many-body systems, it's not sufficient to only understand the static properties, but it's also very interesting, and sometimes the only non-trivial aspects are actually contained in the dynamics. So I'll give you an example for that. Then I will tell you how this can be explored, this kind of physical ideas on digital quantum simulators with midcircuit readout. I choose here, due to my upbringing, dual species Rydberg atoms, but of course you can choose any other platform that you like that features these capabilities. So I will talk about quantum trajectories, how they naturally appear in such a context, and how you can understand and classify these quantum trajectories in some sort of thermodynamic frameworks. This will be, let's say, very brief and rough, but just to get the idea, because this is, I think, all we can achieve in this limited time, and then I wrap up. So, what are kinetically constrained systems? So, and for the purpose of this talk, I will focus on spin systems. Very simple scenarios. So I have particles that have two internal states, one down state, one up state. And now I have a certain rate with which these systems individually can undergo a transition, from down to up or from up to down. And of course here in this case where the spins are not seeing each other, they flip independently. But what I can also do on the other hand, I can introduce a kinetic constraint. And in practice, of course, we will see this also later, this is somehow engineered due to some kind of resonance condition on some, in terms of energy, but just you can also introduce it by hand, and some possible choice of a kinetic constraint would be the following. So let's consider now those two spins, and you say that the right spin here can only flip up and down, provided that the spin on the left is in the excited state, in the up state. So this is a kinetic constraint, so to say you have conditioned spin flips in the system. So if you wanted to look up this model in the literature, you would find it under the name East model. So now, what you can now do is you can plot the dynamics. So this is a trajectory, and those will haunt us for the rest of the talk. Here on the x-axis, so you see basically is classical system containing 100 spins. Let's say each black dot means that the spin is pointing up, each white dot means that the spin is pointing down, and then you see our non-interacting system here on the left evolves, well, in a completely uncorrelated fashion as expected, right? This is just noise that you see here. So on the right-hand side, you see, well, the system evolves rather differently. So we have a strongly correlated dynamic, so you see these structures here, these bubbles in space-time emerging, but this is obviously a manifestation of this kinetic constraint, because certain spins are only allowed to change their state if their neighbor is in an appropriate configuration, right? Now I think, obviously, this is different dynamics, but what I will tell you is that if you look for long enough times in the stationary state, in fact, the stationary state of both those systems is the same. It's not obvious when you look at these trajectories, and difficult to believe. I show you an example in a minute where you can see this more formally. but this is, so to say, the idea. Yeah? So that to illustrate the take-home message, dynamics is more than statics, and trivial stationary, possibly equilibrium state does not mean that the system evolves in a trivial state or is, for instance, non-interacting effectively. So this is relevant, and I have to build a long bridge now here, for instance, in the context of glasses, yeah, where you use these kinetic constraints to model certain classes of kinetic glass formers, they are called. Bottom line is that when you introduce these kinetic constraints, the evolution, the relaxation to equilibrium is dramatically slowed down because, yes, you cannot just switch from configuration to configuration. You have to walk through very, so to say, sophisticated paths into your configuration space in order to reach stationarity or equilibrium. So now some questions that relate to this talk. So how can one study this in the context of quantum many-body physics? So far what I've shown you is all classical. How can we realize kinetic constraints? How do we obtain trajectories? So somehow we have to look at quantum systems, and well, this doesn't come for free, so we will change the state of the system per se, but I will show you how this can be done. Then there's the obvious question how to study large systems and long times. I won't give you a direct answer, I just show you that we can do it. And then the question that is really overarching, well, what to study. And okay, here come the ideas. So the quantum simulation platform, and I felt obliged to choose one because we are here in this quantum simulation session, that I selected is a so-called dual species Rydberg atom array. So what it means is that you have basically a tweezer array, where these sides are paired in a way that in the blue side, certain system species is sitting, and in the yellow side, so-called ancilla species is sitting. So these systems have been introduced by Hannes Bernien, who is now in Innsbruck, actually. And what you basically can do is some constraints, of course, but as a theoretician, I don't have to care too much, is you can basically independently control the interaction between the blue atoms and also the interaction between the blue and the yellow atoms, so which is very nice. And you can also read out the state of these ancilla atoms at any point in time, in principle, through measurements. Of course, this is not true, but details. And if you don't want to use this platform, please use another one. It's all fine. But I just want to use this to make my point. And what I want to say, and very briefly show you that, in fact, these blue atoms, these blue Rydberg atoms, can implement a kinetically constrained atom. So typically what you would do is you would write down a Hamiltonian for these blue atoms that looks like this. So where you have here spin matrices, and this is n is the projector onto the up state, which you identify as a Rydberg state, and then this first term here is just modeling a resonant laser, so resonant to the single atom transition, which can promote one atom from the ground state to the Rydberg state. So this is what's done by this term. But now you see you have this interaction, and this interaction hits as soon, strength V, as soon as one of these atoms is excited to the Rydberg state. Here it shows the left, and then you see, well, suddenly this transition becomes off-resonant. Probably you've seen this 1,000 times. This is also going under the name Rydberg blockade, but here you see how, so to say, merely due to energetic considerations, these kinetic constraints emerge relatively naturally on these Rydberg atom platforms. So now, we have the second system, which is the ancilla system, and this we use to monitor what's going on in our blue system, in the kinetically constrained system. So how do we do this? Also don't want to leave here too many details, but the point is that I have to have an interaction between my auxiliary system and the system that I want to probe. And what I do is basically I implement a conditioned spin flip of the yellow atoms when either of these blue atoms here is in the ground state. And so since you have for each blue atom an ancilla atom, you can track by subsequently measuring the ancilla atoms whether one of the system atoms has been in the ground state or in the Rydberg state. So this would be called also a weak measurement. In the end, this is also equivalent to a so-called collision model of open system dynamics. Choose the terminology that you like, but the point is that we use, so to say, these ancillar atoms which you can monitor as a means to probe what's going on in this blue system of interest, in this blue kinetically constrained system. So now, this is all for the sake of illustration here, discrete time dynamics. So what does it mean? Well, we evolve the system under the Hamiltonian over a time step t. So then perform an ancillar measurement, reset the ancillars, and do another unitary time evolution. And if you look at the reduced density matrix of the system, so the blue one here, then it would, so to say, be propagated from one time step to the next by this relationship. So here's our system state at a certain time, k times delta t. The ancillars are all in the zero state. Then I propagate with this Hamiltonian that I showed you before, and I trace over the ancillars and get the system rho. But I don't have to trace, yeah? This is the whole point. I will show in a second that I don't have to trace, so I really can measure what the ancillars do before the reset of the ancillars again to this vacuum state. But the point I want to make here is if you are looking at this density matrix, you find that for long times, yeah, when you let this propagate to the stationary state, you find this stationary state is as trivial as it gets. Yeah? It's just proportional to the identity. It's completely structureless. All configurations of these blue atoms will appear with equal weight. So it doesn't get simpler as this, or more trivial as this. So in the stationary state, we don't see anything. This is why we want to look at the ancillars, yeah, after each time step. And I just want to tell you basically now how these system observables and the ancillar measurement outcomes kind of go together. So for the sake of illustration, so number is not important, I show you a configuration or a trajectory here for a system which is, let's say, moderately strongly interacting. So the interaction strength is 2 times omega. So what you see here is the following. So here we have 60 Rydberg atoms of the system. Here we have evolution time on 2,000 steps. And what you see here as blue color-coded is the excitation density locally resolved. So I can basically say for each atom, what is the probability for the atom to be in the Rydberg state? Yeah? So with this expectation value. I mean, this is a number I can compute on a computer when I basically tell the computer to solve this equation of motion or to propagate this density matrix. But this is a number which is not possible to access, so to say, in reality, because you have here quantum expectation values. And in order to be able to access this, you would have to repeat measurements exactly, so to say, have the same trajectory, and then, so to say, gather statistics. This is impossible. Yeah? This is also this post-selection barrier that you get when you're looking, for instance, at entanglement phase transitions. Instead, what you get in a single shot, and this is important now, is a trajectory on these ancillars. Yeah? So this is also a system now that has 60 atoms, 60 qubits, which can be now here white or red. And red means simply that this ancillar has gone after the interaction with the system from the 0 state to the 1 state. So every time I measure an ancillar in the 1 state, after a time step, I mark it as red, whereas if it stays in the 0 state, I mark it as white. So, and this is a measurement record that I get always in between these time steps before I reset the ancillars and repeat, so to say, this discrete time dynamics here. So, again, I want to repeat, not accessible, accessible. Yeah, fundamentally different, those two things. So now, you can ask, so what? Yeah, this obviously doesn't look very interesting. Yeah, so this is just somehow very noisy, spins flip up and down in a not very correlated fashion. But now what you can do is you can increase the interaction strength and you implement, so to say, this kinetic constraint. And what you see there is, indeed, well, some funny stuff is happening. Yeah, so you have some space-time structure here, which, well, appears worthwhile exploring. So what we see here, and again, I show always these two plots, the inaccessible ones and the accessible ones. What you see here is that the system is not relaxing uniformly across space. Yeah? You see, you have what is called dynamic heterogeneity. That means we have space-time regions, yeah, these blue ones here, these shaded blue ones, which are active, meaning that there's a lot of change, so to say, of the system. And we have space-time regions which we call inactive, where there hardly is anything changing. And we see this space-time structure of our quantum system also directly reflected for these parameters in the measurement outcomes of the ancilla. Yeah, you see very nicely that these inactive regions here manifest as these white bubbles, yeah, in space-time. So, and now let's try to understand a little bit about the statistics, yeah, and you will see in a minute where this goes to. So we can now ask, what's actually the probability to find an inactive region of certain size, yeah, such a bubble which has a spatial extent L and temporal length tau. And what you do is you make an ansatz. Well, you can simulate this, make an ansatz, and you say, well, we make an ansatz for these probabilities, for this probability of the following form. So we have here one part that corresponds to area scaling. You see that goes as e to the minus some number L times tau. So this is basically the area here. And we have here another part which is perimeter scaling. So this, so to say, captures areas that have an extent tau and a length t, so to say, independently. Yeah, so this is the parameterization that we make. And what you find then is that indeed for small bubbles, you find an area scaling. So this is a not too easy to read plot. So basically this is the probability to find a bubble of area L times t, tau. Here is tau, and here there are different L's. Yeah? But okay, bottom line is, for small bubbles, so with small area L times tau, area L times tau, you find this area scaling, and for large bubbles, you find that actually this scales with the perimeter. And in fact, if you look at this, it's even funnier. So now if you go to even larger bubbles in time, there's apparently another crossover to area scaling. So now you can ask, okay, why is he telling me this? You should always ask this. So, because there's something that is called hydrophobicity effect, which appears in liquid vapor phase transitions, near first order phase transitions, so where liquid converts into vapor and vice versa. And what we find there, yeah, if we now, let's say for the sake of simplicity, think of this as of a 2D system, we will come to this again, where this active phase is liquid and where this inactive phase is vapor. Now, if you ask, what's actually the cost to insert, so to say, the probability cost to insert such a void area here, so could think of some particle that is sitting in our liquid vapor mixture. So what's the cost of inserting it there? And then you will find, yeah, this is so to say the statement of this hydrophobicity, that for small particles the cost is entropic, yeah, so you can always place it in there and the liquid will go around it. And this is, so to say, the free energy of this scale, so to say, as the area, and suppresses, and this is reflected in this probability. And if you have now larger particles, what happens is that it's actually more free energy efficient, so to say, for the system to create a large bubble, yeah, of the vapor phase and place, so to say, and build an interface. And inside this bubble, you place this particle. And the cost of this interface, actually, that it creates is simply the perimeter scaling that we saw in this other plot before. So also what you can show is that if you place these two particles in this fictitious two-dimensional system, they tend to be attracted. Yeah, so this is also funny. Yeah? So this is also a manifestation of this hydrophobic effect. Okay, so now you ask, hey, space and time, and now suddenly he's talking about liquid vapor, so how does this go together? And again, we have only 25 minutes. This is why I couldn't tell the whole story. But there is a bigger picture here. Yeah? So and this bigger picture establishes, so to say, a direct connection between these trajectories that I've shown you now in 1+1 space-time, where the vertical axis was space, the horizontal axis was time, with, so to say, microstates of a fictitious two-dimensional lattice gas. This is, so to say, the connection. And this goes under the name thermodynamics of quantum trajectories, quantum jump trajectories. And I invite you to read our paper that we wrote by now 15 years ago. But so to say, what you can do here, and I think now with this plot, you see it in a sort of convincing fashion. You can now interpret, and this is wrong, so this should be liquid. You should interpret this phase, so to say, for this interaction strength as the vapor phase, and liquid phase, sorry, and this phase here where you have these bubbles, of vapor as vapor-liquid coexistence at, so to say, a first order transition. So you can ask now, how does this go formally? And for those of you who are tired, just listen to me, don't look at the formulas. So I very briefly want to illustrate what the underlying thinking is about this thermodynamics, and now how we can also relate this to first order phase transitions here. So what you can do is you can define some kind of dynamical order parameter. So for the magnets we have heard before, so we can define the magnetization. Here what we can do is we can define, so to say, the number of flips, or per time. How often do my ancillas change their state from 0 to 1 over a certain interval of time and a certain length of space? So this could be an order parameter. It's very similar to the magnetization. And what you can then do is you can build some kind of canonical ensemble, which is basically composed out of an a priori probability of each of those trajectories times a weighting factor, which goes with this observable, with this dynamical order parameter. So which reweights, so to say, these a priori probabilities with a value of this that depends on the order parameter that is weighted by a conjugate field. So it's really thermodynamics 101 transferred to this kind of open system dynamics that is unraveling here in space-time. What you can then also do is you can take this object and you can calculate a partition function, and for large time, so long enough trajectories, you can also then define a so-called entropy density, and you can basically draw from this construction, details don't matter, a phase diagram, where we have here the conjugate parameter, think of this as, I don't know, temperature, for instance, and here the interaction strength. It's not real temperature, so it's something that lives in this space-time, that controls the dynamics in this space-time that I'm showing you here. But I just want to make the point that now we are in reality sitting, so to say, at this point. So my dynamics, my unbiased dynamics takes place here at s equals to 0. And basically, what I do is by going to the left is I make active trajectories more likely. If I go to the right, I make inactive trajectories more likely. And here's the interaction strength. And what you see now, if you walk now up here, you see there are these lobes coming in. And okay, without much explanation, you see that here there's a lobe touching, so to say, this s equals to 0 line. And this is basically a point where these inactive trajectories start to become likely. So actually, I'll show you in the next slide, they start coexisting with this liquid trajectories. And you can also make a plot, you can do some kind of phi scaling, but you see, so to say, when you go along this line here, you get a jump, which is reminiscent of a first order phase transition that you also know in equilibrium thermodynamics. Again, cut away all the details, you can give a whole lecture course on this. But this is, so to say, the idea. Thermodynamics in space-time you can apply here. So, and in fact, you can now look at this coexistence more directly, not in this kind of intricate phase diagram, but you can really ask, so to say, now, what is the number of, what is the probability distribution of my order parameter, which is, so to say, the number of flipped ancillas on these space-time trajectories. And for this, you can go from this partition function here, you can convert this into a probability distribution for this count rate as a Legendre transform. Again, it's all thermodynamics. And then you see the probability for observing a number of up ancillas per time goes as e to the minus t. So t is here, so to say, the extensive quantity, which in equilibrium thermodynamics would be a particle number or volume. And this is then multiplied here by free energy density. And you see now, this phi here determines, so to say, the probability yeah, with which certain count rates appear. So, and now, this is the last thing we need to understand. So T is very large. So this is dominated by points where phi is very small. So you see here, here's a certain count rate. Yeah, so this is exactly this phi. It's a bit funny, yeah? But it's really just a log of this probability distribution and a minus sign. Then you see here, here's apparently a minimum, yeah, which at a certain count rate, and this corresponds to counts that correspond to active trajectories. Yeah? This is kind of this liquid part. And then you see as the system size increases, and Maria's done it, I see her here, right? When the system size increases, you see there's another minimum coming down here at 0, approaching 0. So it's also basically a peak, if you translate this, in the probability distribution, which is at 0 activity, yeah, which is basically corresponding to this vapor phase. And what you then see here is an extremely broad distribution, so one peak and another peak here, linked by some horizontal line, and this is exactly the Maxwell construction that you know, yeah, from first-order phase transitions. So I'm coming to the end. Yeah. So I hope I could convince you that this is a nice playground here to do fun stuff with open systems and link it to concepts in thermodynamics. There's a lot of stuff to ask here. What about more complex interactions? What about the role of quantum effects, which I have completely swept under the carpet? I pretended that everything could be calculated for large sizes as on demand. How to do experiments is also an open question. And this is a question we are currently trying to address here within an ERC synergy grant together with Ferdinand Schmidt-Kahler and Markus Henrich, where we use trapped Rydberg ions, actually, which allow to simulate such quantum dynamics over extremely long times to implement kinetic constraints, look at these glassiness, dynamic phase coexistence. So, and this comes also, of course, with postdoc and PhD opportunities. Please inquire. Thank you very much.
All right, thanks for this talk. Are there questions?
So this, what was it, kinetic constraint you imposed in the beginning vaguely reminded me of cellular automata.
Sure. Yeah.
Is there some connection, or is there...
Absolutely.
Is this complete? Okay.
No, absolutely. I mean, all this discrete time business that I showed you, in the classical limit, that there's a one-to-one mapping on cellular automata, absolutely, yes.
But then these trajectories that you showed looked much more random than what a cellular
Okay, this is why you have to add the word probabilistic in front of the cellular automata, sure, yeah. Okay. So, I mean, the relationship is more, it's not to this kind of Wolfram rules, so to say, but rather to Domani-Kinzel cellular automata, yeah, which are probabilistic ones and which are very closely linked to dynamics of that kind.
Okay.
There's one question there in the back.
I'll never get used to this. So I feel like your framework is kind of similar to a measurement-induced phase transition. The difference is instead of using random unitaries, you're kind of...
Well, the difference is that you can measure it.
Oh,
this, I would say, is
so instead of like attaching ancillas and doing weak measurements, we're actually using a different species of neutral atoms to actually see, right? Whenever a disentangling event happens, I think that's...
Entanglement is not so much of an issue here. Yeah? So I mean, also because we are not actually even probing the state of the system. We are only probing the state of the output. Yeah, and this is different. Yeah. So, but of course, it's somehow still a transition in the way, so to say, this kind of open system dynamics is unraveling. Yeah, it is related, of course, to this measurement-induced phase transition idea. Or I would maybe turn it the other way around. The measurement-induced phase transition idea is related to this. But we are not looking at properties like entanglement entropies, for instance, in these systems.
Yeah, yes, of course. What they do is they simulate it, right? They focus on, you know, E, I don't know, 1, 2, 3, extrapolate. But what we do, I mean, I briefly looked at the Hamiltonian here, And whenever you measure the ancilla in 1, what you're essentially doing is you're projecting the system, you're kicking the system back out to 0, projecting it to a product state, right?
Indeed.
Disentangling it. So in that sense, it's quite similar. And so therefore, my question is, all the tuning that I've seen on this presentation has been omega over v, right?
Yes.
That's the system Hamiltonian. Is there any tuning with the measurement strength, with
No.
gamma?
No. We have not looked at this. And this is also, I would say, this distinguishing factor. But this is, so to say, what I vaguely mentioned at the very end when I talked about here quantum effects. Yeah. So this is exactly, so to say, the handle, yeah, with which to control quantum effects. Because you're rightly saying that if, of course, this measurement rate is large, I keep entanglement down. This is, by the way, why I could show you such big trajectories also. Yeah.
Cool. Thanks.
All right, thanks. I think in the interest of time, we should move on and thank Igor again for this very nice talk. And there will be another